Hey, good morning, everyone. So I'm very happy to introduce Steve Markham from the NEAST Observatory today. So he'll talk about chaotic meteorology in the atmosphere and interiors of gas-giant planets. Steve, take it away.
Okay, hi everyone. Thanks for inviting me. I'm going to be talking about a few things that happen in the atmospheres and interiors of giant planets as a consequence of there being continuous fluids that are very different from the way we think about those same processes happening on Earth. So the motivation here is just to sort of take a step back from the considerable advances that we've made in thinking about atmospheric and interior sciences, which developed intellectually primarily around the Earth. The traditions of atmospheric science on giant planets have their roots in Earth atmospheric science as well as oceanography. But there are a few fundamental differences between the processes as they occur on Earth and as we expect them to occur in giant planets. And I'm just going to inspect a couple specific problems and how they have consequences that we didn't expect when we thought about them before. So I'm sort of simplifying to say, what are the differences between Earth and gas planets? So the first is that Earth has a surface, whereas gas planets have no surface. Earth has one condensing species, that is water, whereas gas planets can have many condensing species. And I'll talk a little bit more about why that matters. And Earth has a nitrogen atmosphere predominantly, whereas giant planets, gas planets, have hydrogen atmospheres. So I'm going to start by focusing on one of these particular differences, and that is the existence of a surface on Earth compared to the absence of a surface on giant planets and how that makes a difference. So on Earth, we're all familiar with the water cycle. It's a very complicated thing. You have clouds that condense in the sky and they rain down onto the Earth. And this Earth pools and it falls as snow onto the mountaintops, runs down in rivers into a complicated hydrological cycle that some evaporates, some ends up in groundwater, some is affected by life. It's all very complicated, and modeling it is a challenge for scientists who are interested in this. And for a long time, the scientific community interested in the hydrological cycles on giant planets thought that the absence of the surface is going to make things considerably easier. Because without the surface, you can cut out all of the complex hydrology and oceanography and focus purely on this relatively simple looking picture. The idea is that the precipitation will fall, and even though there's no ground to stop it from falling, it will eventually vaporize. The reason for this is because of the adiabatic lapse rate that exists in compressible materials. You have Death Valley, California, that is extremely hot. You have the top of Mount Everest that's extremely cold. You imagine if there's no surface, you can downward continue that trend, and eventually it's so hot that you're going to boil water. And once it boils, it's no longer rain, it's gas, and gases mix together in all proportions. So once you reach that level, everything is going to be nicely well mixed, and the hydrological cycle is going to be very simple. That's what we thought for a long time. I'm going to inspect that question a little bit in light of some of the new observational evidence we have of Jupiter to see if that is a good way of thinking about this problem. Now, we actually have some instances on the Earth where vaporization happens before it reaches the ground. In some dry and hot desert regions, for example, my native New Mexico, you have this phenomenon called virgas, where you have rainfall and that vaporizes before it hits the ground. And there's already a little bit of a warning here, because we know when virgas occur that just because the rain vaporizes doesn't mean it stops falling. You have now condensed rain. The latent heat that's released means it's going to be cooler than its surroundings, and it has momentum because it was just falling. So it actually continues falling and is associated with cool winds on the surface. It stops on the surface and spreads out. So this is already sort of challenging the assumption that just because it vaporizes means it stops falling. Now, the observation that is key for Jupiter comes from the Juno mission, which Ravit here is involved in, and the observation from its microwave radiometer that has probed beneath the surface in order to try to constrain its composition. And what was unexpectedly found is that ammonia is significantly depleted beneath its condensation level. So you can see here where ammonia, its blue colors are low ammonia, white colors are intermediate, and dark red colors are higher concentrations of ammonia. What was essentially expected is that you'd have this blue colors over here, which is above the cloud tops. It condenses, so it no longer exists in the vapor phase. And then around here where it vaporizes, then you will have some kind of constant composition. Instead, you find that for tens of bars, there are, in fact, this persistently depleted in ammonia region. And this is difficult to explain because how does the ammonia that's in the vapor phase fall without mixing with its environment? Everything is turbulent, and so you expect mixing to be very efficient. What's going on? So part of the answer that has been investigated in the past is something that I mentioned before, that you have multiple species that are condensing in the atmosphere. You think of giant planets as predominantly hydrogen, but they're polluted with remnants of the early solar system or impacts that happened subsequently in the solar system's history. And there's all sorts of chemistry going on in there. So you have water clouds and ammonia clouds, which I mentioned before. And these will interact chemically. And they can actually form a combined phase that acts as an antifreeze. And this has important applications for understanding the hydrology. So I've embedded this YouTube video. This almost never works, but let's see. All right, great. So Tristan Guyot, who's my advisor at Nice Observatory, came up with this idea of mush balls. What you're seeing here is an ammonia raindrop falling. And as it falls, it absorbs water from its surroundings, which acts as a way to prevent vaporization. And then it begins to acquire an ice shell as it continues to fall, and water begins freezing around it. Now, as it continues to fall and below the water cloud level, the water will start vaporizing off of the top, but protecting the ammonia on the inside before eventually the ammonia vaporizes. And then, as the assumption goes, now that it's vapor, it'll now mix with its environment. And the idea is that these thick hailstone-like particles are able to fall through these 100-kilometer distances without efficiently mixing with their environment because they are not vaporizing. So I'm interested in the same problem, but not all. This solution is unique to this sort of chemical interaction that occurs between these two species. But there are other planets that, for example, Uranus and Neptune, that have weather going on in the methane cloud layer, and we don't expect the same interplay between other species to be relevant. But I'm wondering if maybe the results from the Juno mission are hinting at something more fundamental about the fluid dynamics of how rain is expected to operate without the existence of a surface. So the idea here is that we have very simple analytical models that go back to the 1950s about how rainstorms exist on the Earth. And they go back to some experiments where you look at how density currents evolve in a tank by having a tank of water, dropping saline water into it. The densities are negative, but it should be symmetrical, and you can infer how things evolve. And when you have localized sources of density anomalies, it will naturally form a vortex ring that will propagate as a coherent quantity. So this is the context that I'm looking at. Here, instead of imagining everything as just homogeneously turbulent, we actually know from observations that you have discrete storms that are happening on Jupiter. And so you know that you have discrete rainfall that happens in concentrated thunderstorms, the same way we have on Earth. And so you expect these types of dynamics to be relevant, these sort of localized downdrafts. And the motivation here is that because of the increase in pressure as you fall, you have two competing effects. On the one hand, you have the tendency of these vortex rings to turbulently entrain their surroundings and thereby mix with their environment. However, you have the competing effect of the compression of the atmosphere that will tend to shrink, that will do work on these downwelling thermals and compress them. So if you're looking at the volume that you expect this material to take, there are two relevant parameters. The first is the entrainment parameter, and the second is the compression that happens from the environment. And so you can, just writing down this very simple equation, you can imagine, okay, this term's negative, this term's positive. What's going to matter is the relative magnitude of these two terms. And that indeed turns out to be the case. And as I was doing this research, I came across some of the literature in the context of the sun that has invoked a similar idea to explain some observations on the sun that I won't get into too much detail, but essentially, if you assume everything is homogeneously convecting on the sun, then you expect certain flow velocities. But what has actually been observed by helioseismology measurements is a lower convective velocities than are required to accommodate the solar luminosity. So the idea is maybe you have these things that are these small localized downdrafts that are being missed by these large scale motions that are responsible for some significant fraction of the sun's cooling. So this is what they pointed out is similar to what we point out. And they run these simulations in the non-turbulent limit and find that indeed you have what they call a stalling versus a falling regime. So in the stalling regime, as you fall, you mix with your environment, eventually you mix, and you have dynamics that are similar to what we think of when we think of homogeneous convection. However, if you are in a compressible enough environment, then you can continue falling and not really mix with the environment very efficiently at all. So we went ahead and did our own simulations, but we know that the environment should be turbulent. So we used this software simulating non-hydrostatic atmospheres and planets to look at the same initial conditions, but to resolve the turbulence. And we find that there's actually a difference. So we're able to reproduce their results here on the left-hand side when we use sufficiently low resolution that is not resolving the turbulence and is thereby sort of numerically artificially increasing the viscosity of the system. But when we do higher resolution simulations that resolve some of the turbulent instabilities that occur, you find that there eventually reaches a hydrodynamic instability that breaks apart this coherent vortex ring. So if you look at the evolution of this dense material as a function of time, you see the difference between the low resolution runs and the high resolution runs, and you also see that the analytic predictions work pretty well. So, okay, now we want to look at how this all can be summarized onto a single plot, because you have, each of these simulations have 200 gigabytes of output data, but you want to reduce it all to one number. So we got to come up with some way to do that. And so from the plot you saw on the previous slide, this is a simplified way of thinking about it. You have the centroid of the system, you have, and its distribution of material. So 1 sigma, 2 sigma, 3 sigma, represents where all the material is. So basically, most of the material is within this 1 sigma bound. And you have to define some depth at which you say most of the material ends up sort of below this depth and doesn't mix very efficiently above that depth. And we find that it's able to propagate down to several multiples of its initial size. And if its initial size is comparable to the scale height, then this can be several multiples of the scale height. You can see them right here. Okay, so now I've summarized changing the parameters as different sizes, and what you see is actually contrary to our original hypothesis that this compressional effect would allow the perturbation to propagate deeper by keeping it concentrated spatially. And that's because of a breakdown in our assumptions of linear theory that are produced by turbulence. So it does actually follow the analytic predictions at first as it compresses itself, but when it does so, it creates shear instabilities that are so extreme that it breaks itself apart. So if you look at the initial size of the perturbation, so here on the x-axis, you have non-dimensionalized time. Because the dynamics are dependent on the size of the initial system, you wouldn't really be able to compare these different curves directly, but if you non-dimensionalize it, they're all pretty close, and you can see the important differences. So this is non-dimensional time, and this is non-dimensional depth. And you see this orange curve is the largest initial perturbation relative to the scale height, and this dark blue colored curve on the bottom is the smallest compared to the original scale height. And so you see that our hypothesis has sort of been debunked a little bit. Then the second thing to consider is just another way of defining the penetration depth, because it's a little bit arbitrary. It's just choosing some number to describe a complex simulation. And so we came up with an alternative thing to make sure we weren't biasing our results too much based on our specific choices. And so another way you could think about it is as you have this density perturbation, it initially accelerates, but as the instability ensues, the downward propagation ceases to be coherent and the centroid ceases to subside at the same velocity. So you can pick some cutoff it's a little bit ad hoc, but say -0.2 in these non-dimensional units, and you can define that to be the penetration depth. And this gives us our results that are the penetration depth as a function of size. We're mostly at this stage, because this is the first time anyone's really thought about this problem, interested in the orders of magnitude. And we find that there is what I had mentioned before, that the larger you are relative to the local scale height, the less distance you go relative to your initial size. However, because you're larger, you are bound to propagate further because you are a larger coherent structure in the first place. So when we combine all this together, we come to the conclusion that under realistic storm conditions on Jupiter, you are able to propagate through the 100-kilometer tens of bars that you would need in order to explain the Juno MWR observations. And so this now offers a second sort of either competing or complementary theory to the mushball hypothesis. The reason being that it could be complementary is because the mushballs vaporize at a certain point, but they can continue going down after that point. We think that the mushballs really do exist, but whether they're central to this depletion or whether this hydrodynamic argument is central to the depletion is an open question. So we considered some confounding factors. We made particular assumptions that were contrived in our initial conditions. We also looked at different computational methods to see to what extent they affected our results. And we found that almost no matter what we did, the basic conclusion that you see this stuff starts up here and it goes pretty deep before it actually starts mixing with the environment. That's the important result. It's more of a qualitative than quantitative result, but the orders of magnitude are sufficient to explain the observations. Okay, so here's the conclusions. Rain cannot fall forever. It does stop eventually. This is contrary to previous claims, but it can continue falling even after vaporizing, and it can fall for very significant distances. And it can also fall enough to explain the Juno observations by fluid dynamical arguments alone. You don't need to invoke any chemistry. And the storm length scales compared to the density scale height matters. So you can't directly use the scaling relationships from the water tank experiments in the 50s. You can't simulate you can't do an experiment for the compressibility on the Earth because the Earth isn't tall enough. It's not as tall as these giant planets, the column of the atmosphere. And volatile depletion may not be unique to Jupiter. So it might be also relevant to Uranus, which is of, I think, high interest because it can also apply to exoplanets. Right now, there's a big push going on in the exoplanet community to try to quantify the abundances in the atmospheres of gas planets all over the galaxy. This is great, but this is a caution that what is measured in the atmosphere is not necessarily what is actually the abundance in the bulk envelope of these gas planets. So this, how am I doing on time? Oh, I have plenty of time. Okay, I went a little fast, so feel free to stop me. Okay, so now I'm going to focus on a second fundamental difference between Earth's atmosphere and gas planet atmospheres, and this is the composition, nitrogen and hydrogen. Now, at first glance, why would this be important? They're both gases. They can be treated as gases. Why does this composition matter in the context of fluid dynamics? Well, it matters because hydrogen is the lightest form of baryonic matter that exists in the universe. And that means that any other system, any other chemical that is coexisting with it will be heavier than the hydrogen. And this has some consequences when you have multiple species condensing within it. And to sort of think through what these consequences are, I invite you to do a thought experiment where you imagine a planet where there is an ocean, a planet much like Earth, but instead of a nitrogen atmosphere, we instead have a hydrogen atmosphere. And imagine what is going to be happening at the surface of the ocean with the density of the hydrogen. So at very cold temperatures, it's going to behave exactly like an ideal gas. As you increase the temperature, you increase the specific volume, and this is because the kinetic energy of the molecules increase, and therefore their expected distance from each other will increase. Now, as you continue to increase the temperature, that continues to be true. You increase the intermolecular spacing linearly. However, because it's in contact with a reservoir of water, then as the temperature increases, water vapor can begin to enter the system. So even though the specific volume is increasing, so too is the mean molecular weight as the composition changes. As you continue heating up the system, the water abundance will increase in a Arrhenius relationship, which overwhelms the linear relationship of the mere specific volume. So inevitably, there comes a turnover point, after which, if you increase the temperature of the gas, you also increase its density. That's the point. Okay, and there's actually, this has been studied in the context of planetary atmospheres, especially for Uranus and Neptune, where we believe that the abundances of methane are sufficient for this effect to be relevant. And this is some work from the original Voyager measurements of Uranus, and that show that the atmospheric structure is actually not very well constrained. You have to assume some kind of model for the atmospheric structure, and what was originally assumed was that it would behave adiabatically. However, Tristan Guyot in the 90s pointed out what I just pointed out now, that if you are changing the composition as you change the temperature, then you can stabilize against convection, and demonstrated that the Voyager measurements are consistent with such an atmospheric structure. More recently, there has been renewed interest in this phenomenon as it applies to the ice giants and the upcoming proposed mission, flagship NASA mission, to the ice giants, as well as exoplanets that appear to have this effect be very relevant. So the simple idea of just how does density evolve as a function of temperature is just the first step. You need to actually evaluate the stability under more realistic conditions where you have finite timescales on which vaporization and condensation and rainout can occur. And the upshot of these theoretical studies has been that this is not only stable against ordinary overturning convection, but also against double diffusive convection. And it's robust under realistic assumptions. I've also recently been conducting some preliminary simulations, as has Chung Lee and one of the students at the University of Michigan. They're actually have just submitted a paper to be published on this topic. And the preliminary simulations seem to indicate that indeed this effect is produced as an emergent phenomenon using realistic microphysical schemes for the behavior of the planets. And without using it as an assumption. You know, there are two different ways you can make models. You can either assume like, okay, this is the stability criterion, and so if there's some stabilization, it's in some sense an input. This is completely agnostic. You don't assume that stabilization is going to happen. You merely say, here's hydrogen, here's water, let's cool it from the top like it happens on planets, and let's see what happens. And you find that the predicted stabilization around the cloud level is reproduced by these simulations. So this gives us an idea that perhaps this idea should be taken a little bit seriously. And so I investigated how this may be relevant in the atmospheres of Uranus and Neptune. And I found that that it has implications for the thermal evolution of the planet. Because you can convectively decouple the atmosphere of the planet from its interior, you can change its luminosity throughout its evolution, and this changes the predictions for the dynamics of its cooling. So this should be considered if you are using hydrogen planets that are significantly polluted with volatiles. You should consider this effect of convective inhibition. So yeah, this is preliminary work, and this is this an open question. There have been some, like Jim Friedson, who have suggested that you have this stable layer, but it can be eroded by entrainment, and under certain conditions may eventually become too thin and therefore susceptible to overturning convection. I think that that is based on what I've looked into, I think that this thinning will create a temperature gradient that allows more heat to escape into the exterior, can trigger convective events that can sort of leach materials back into the atmosphere and then sort of replenish it. But it's poorly understood at the moment. Actually, I don't want to scoop Chung's results because they're not published yet, but the simulations seem to indicate that it may behave sort of more like a relaxation oscillator, in which case that would corroborate a 2014 theory that is responsible for some sort of explosive quasi-periodic giant storms that have been observed on Saturn. So the details of the exact dynamics are still being worked out, but on the time scale that I'm showing here, this is just, you know, a few days, and on this time scale, it's certainly stable for the entire time. But if you do the simulation for centuries, it might not be. Okay, so now I want to shift gears and talk a little bit about exoplanets. When I first introduced this idea, I discussed a thought experiment where you imagined an ocean. And an ocean is different from a giant planet atmosphere because there is an actual surface, and the surface acts as an infinite reservoir of condensing species. So as you increase the temperature, you increase the composition, but you eventually run into a problem. You still have the turnover point, but you eventually reach the boiling point. And so within this region, you have convective inhibition, but above this region, you will instead encounter a steam atmosphere. But now let's continue and think about how exoplanets that we've observed actually behave. Let's think about super Earth sub-Neptune type bodies, for example. And these are thought to have a global magma ocean overlain by a very significant hydrogen-helium envelope that is of the order of kilobars in pressure. And in this case, you actually begin to exceed the critical point of water, and you can't use these simple ideal gas arguments anymore. What happens in this case? So you can't use these same arguments, because when you're above the critical point, you can mix these condensing species and the gases in all proportions. Supercritical fluids will mix in all proportions. And so you need to look at more specific thermodynamics, and for that you require experiments. So these are some experiments for a hydrogen and water coexistence conducted in the 80s by Seward and Frank. And it gives you an idea for the behavior of how these types of systems evolve. So the way to think about this is that you have on this side, pure hydrogen, and on this side, pure helium. Sorry, pure hydrogen, and on this side, pure water. At low pressures, then the ideal gas approximation is relatively accurate. But as you go to higher and higher pressures, you instead find, instead of a pure liquid that exists on this side and a gas that's increasingly polluted with water vapor, you instead find a more equal distribution, where as you increase the temperature, you have two coexisting phases on either side of these diagrams, and the water is both polluted in hydrogen and the hydrogen is polluted in water. And the critical temperature is the very top of this distribution, where they can mix in all proportions. And if you do this steadily, then you expect that that proportional mixture approaches a 50-50, 1-to-1 molecular mixture. So in this system, you can't use the formulations of convective inhibition that have been explored before, which assume that it's an ideal gas that behaves as an Arrhenius relationship. So I just wanted to prove that in the general case, this same effect can exist. And what I do is I define this effective coefficient of thermal expansion. So when do things convect? They convect when the coefficient of thermal expansion is positive. Therefore, hotter materials are less dense, and therefore a hotter material of the same substance underneath colder material of the same substance will be less dense under more dense. That'll be Rayleigh-Taylor unstable. You'll have overturning convection. However, there are materials that don't behave that way. For example, water near its freezing point. In that case, you actually have a negative coefficient of thermal expansion. And as you increase the temperature, you also increase the density. And this is why we observe lakes to freeze from the top instead of freezing from the bottom. So all I've done is taken the same typical a coefficient of thermal expansion, and added some additional terms to account for the fact that the composition is changing. So that's it. The idea is if this is positive, then convection occurs. If it's negative, convection does not. So now we need to think about how the observations for the critical coexistence of hydrogen and water affect our assumptions. So here on the dashed curves, I've taken the ideal gas approximation that you have a hydrogen that is being polluted with water vapor, increasing according to an Arrhenius relationship. So basically, this is just the vapor pressure of water. And then at the critical point, they mix in all proportions. So then you have pure water. So the actual observations, you find a deviation from them. So if you're only slightly above the critical endpoint pressure of water, it's just a small correction. But as you get to higher and higher pressures, the corrections become more and more important. And crucially, the critical temperature is also affected as a function of temperature, and the expected equilibrium mixture between these two substances is also affected. So you see that it's close to 1 when you're just barely above the critical endpoint pressure, but it approaches 50%. So a 1-to-1 molecular mixture as you go to higher and higher pressures. So this leads to this plot here, which shows on the y-axis pressure and on the x-axis temperature. So we're interested in where does convective inhibition happen in pressure temperature space, including under supercritical conditions. So here you have the inhibition curve. This is the top of that specific volume diagram that I showed before. You can just tabulate this and you get a unique curve. Here you have the boiling curve. This is just where the hydrostatic pressure that's relevant, the pressure of the environment is the same as the vapor pressure of the water. And then the behavior changes when you reach this critical endpoint. So this is the critical endpoint pressure, the critical endpoint temperature, and then you have a critical curve that depends on pressure and temperature. And these symbols are from the previous plot. So dot, open, star. And so they show you where they lie along this curve. And you see that you begin to deviate away from this assumption for the inhibition curve. So you will have something that appears more like this. I put these dotted curves to say that these are notional. We don't know exactly how they behave because we don't have the experiments. So let's put these in the context of planets. So water inhibition region, you cross it when you look at the expected interior pressure temperature relationship for Uranus. You cross it with Jupiter. Now with Jupiter, is there actually enough water for this to be relevant? We don't think so, but with Uranus, we think there is. And now what I'm going to focus on is this planet here, Kepler 36c. This is a emblematic sub-Neptune, and it is believed to exist in the state that I described, where you have a magma core overlaid by a hydrogen-helium envelope. And what you see is that the expected interior profile crosses right through the rock inhibition region. So how do you define these? You'll notice I've used dashed curves here. The data is from a ab initio simulations from Lars Stixrud and Xiao that have constrained the critical vapor pressures of rocks. So I haven't actually accounted for the effect of the mixture between rock and hydrogen and how this would affect sort of this lower corner. But you should think that conceptually we expect it to be the same, but at the moment there's no empirical data, so I don't want to draw a misleading curve. But conceptually, the same applies. So we want to constrain how important this is for different planetary atmospheres. And we find that for the atmospheric masses that are expected to be relevant for super Earths early in their evolution and sub-Neptunes later on, that they intersect the rock inhibition region. And this means that as a function of the atmospheric mass, you can define a unique temperature structure that is in equilibrium. And and then it intersects this inhibition region, and then you expect it to be super adiabatic and transition into this supercritical rock and hydrogen mixture. This affects the thermal evolution of the planets. So here you have the planetary heat flux of as a function of the atmospheric mass of these exoplanets, and then with some solar system planets, Earth, Neptune, and Jupiter for reference. And you find that the expected flux is lower for these solid curves compared to the dotted curves, which do not account for this effect. And this has an effect on the expected cooling timescale. So from this, we propose a new model for super Earths that is particularly relevant to the early stages of their evolution, where we propose a new interior structure. Previously, you assumed that there are two layers to these planets. You have the magma core and the hydrogen helium envelope. They are compositionally distinct, and they have a coupled interface. So the magma ocean is fully convective. It has an ocean surface with this compositionally uniform convective envelope, and then a radiative stratosphere where it loses its heat to space, and this core slowly cools and eventually solidifies. So we are instead proposing a new way of thinking about this. So if you start from the top, you have the same principle where you have the radiative stratosphere that turns into an envelope, but where this begins to change is you instead have an envelope that is saturated with rock vapor. As it reaches the pressure at which you stop convecting, then you can support a super adiabatic temperature gradient, and this leads you to a supercritical silicate core. And the prediction is that this supercritical silicate core should have a composition that is 1-to-1 between hydrogen and rock. So the hydrogen, rather than being compositionally distinct, may be intimately mixed with the core. Okay, I think I just described all of these things already in the previous thing. This is just, now they're spheres. Okay, and then there's one other application of this of this general principle that I've started working on, but it's still unpublished. And that is for the coexistence of hydrogen and helium. So this is another example of taking something that we thought was relevant to atmospheric dynamics and applying it to the interior structure of planets. And what we have found is that this coefficient that I described, the effective coefficient of thermal expansion, is essentially negative. So under very high pressures and sufficiently low temperatures, you expect that hydrogen, being on the leftmost column of the periodic table, has a possible structure where it has a ionic mixture, lattice, potentially, and an electron sea. This is how the alkali metals generally exist. Hydrogen, under STP conditions, of course, exists as a gas, but it's been theoretically posited for a long time that this metallic phase can exist. It's recently been claimed that it has been experimentally found. And in this phase, you do not expect that the wave function that corresponds to helium atoms has any place within this metallic lattice, and therefore you expect it to phase separate. So it's conceptually very similar to gas and condensate phase separating. And you can use the same method that I described previously to evaluate whether it is going to increase or decrease in density as you increase the temperature under thermodynamic equilibrium, and you find that it should be stable against convection. So this is something I'm working on. It has a few consequences for Jupiter, but it's not the subject of the talk. So I will move on with my conclusions, is that planets that form with an ocean and envelope may be strongly influenced by convective inhibition, and characterizing convective inhibition should be a scientific priority of a Uranus flagship mission. We think that this is happening at multiple cloud levels in Uranus, and you can do all the simulations and theoretical work you want, but what you really want to see is it actually happening in nature. It's not something that you can simulate in a laboratory because you need a whole atmosphere to do it, but luckily we have this natural laboratory just sitting only 40 cruise years away, or however far long it takes to get there, but relatively close in cosmic terms. And so this should be a priority. And furthermore, that convective inhibition should be considered when interpreting exoplanet atmospheric composition observations. This is happening a lot right now. And so if anyone is working on exoplanets, I urge you to keep this in mind. And yeah, that's all I have.
you, Steve. So we have plenty of time for questions.
Physics going on there. So is this something you only research for ammonia, or is there like this is not going to be so great for one other species in the atmosphere, and then maybe comment why you observe this would be
Okay, well, to what extent do you want the party line, or to what extent do you want my speculation? Okay, well, it has only been formally investigated in the context of the water ammonia system in the planet of Jupiter. It's actually been explored sort of notionally in Saturn and Uranus and Neptune as well, because you expect there to be water and ammonia in those planets as well. I suspect that the interaction between these different cloud levels is going to be critical to understanding what's going on in these planets. For example, you expect there to be silicate clouds, but the chemistry there is extremely complicated. I mean, you have geologists and mineralogists whose entire field is dedicated to just understanding the different ways that silicates can interact chemically. And it's still, even with the Earth, where it's really easy to pick up a rock and analyze it in incredible amounts of detail, and you can evaluate the chemistry in a lot of detail. And it's still something that it is kind of difficult to fully constrain. And I imagine that we have all sorts of chemical interactions that occur in silicates on the Earth, and I imagine that the magma droplets that we expect to be in Jupiter will also interact with all sorts of chemical species and may be crucial to understanding what's going on above them. So the idea is that these cloud levels that are you have a particular cloud level you're interested in, and like ammonia, for example, and you think about it in isolation, and you come up with some kind of prediction of how you expect it to behave, and then the observations don't bear that out, and it turns out, oh right, because there's another cloud level underneath it, and they chemically react with each other. And I think that the water ammonia system is actually a remarkably simple example, because it's just two chemicals that interact in a very well understood way. But I think with silicates, we're going to have a whole mess of things happening. It's going to take many funded positions to disentangle. Yeah.
First, on the first part, when you have this frame, right, you check how deep can you go. What about rotations? Do you have convection in information? Do you have a convective background? But wouldn't cross rotation affect that?
Yeah. Okay. So I'm glad you brought this up. When I originally sought to do this project, that was one of the major motivating factors, was to understand the role of rotation in understanding these dynamics. Unfortunately, doing so with simulations is sufficiently complicated that I decided to exclude it for now, and to revisit it later. But I will make a few comments about how we expect it to be relevant. On the Earth, we observe the most intense mesoscale activity in the mid-latitudes, and in the tropics, we primarily observe what's called quasi-equilibrium tropical meteorology. And this is basically, if you take the simplest assumptions of you have clouds that form nice and puffy and they rain nice and steady, and everything is sort of an equilibrium adiabat everywhere, that's what you get. And in these scenarios, you don't actually produce these types of intense storms that were the initial condition for the simulations that I was doing. So I expect that under those conditions, the analysis that I've conducted is not really relevant. The other thing, though, is that the existence of rotation is fundamentally important for understanding how fluid dynamics evolves. Now, the Rossby number that's relevant to my simulations is such that for these localized events, it might not be important, but it's something that definitely warrants further study.
I was just wondering, for example, when you had the water and hydrogen, that it was just kind of this mixture. But what if I have helium and other elements? How much should I expect them to choose?
That is a good question. I think we need very expensive experiments and very complicated simulations to answer it satisfactorily. Helium, under these conditions, we expect to be relatively inert, so we hope that it doesn't affect the results too much, but actually we need an experiment to say for sure. In terms of and other elements, for example, water, that's another interesting question that is also, unfortunately, at the moment, with the empirical evidence we have, difficult to constrain. It is actually something that has been recently. There's a new published paper by Will Missner and Tilke Schlichting at UCLA, who have looked into the chemistry of the rocks and hydrogens and water. And what they actually find is that that the conclusions I presented here are actually underselling how important this is, and that actually even at lower temperatures you can already have this convective inhibition because of the chemistry that's relevant. So the answer is it's really complicated, and yeah. Are you talking about the depletion of the? Unfortunately, I think it is going to be difficult to have any sort of measurements that are that the scientific community will have 100% confidence in with a probe. I think a companion instrument like MWR would help, and I think a probe at multiple entry sites would help, because if you had multiple probe measurements and if they were both the same, you might say, okay, maybe this is actually representative. But if they're very different and you have active meteorology that's making a difference, then you might say, okay, well, this is interesting for understanding the atmosphere, but it might not be as interesting for understanding the interior. Mm-hmm. Well, this was sort of what motivated my postdoc at Nice was to try to. We've only very recently started to realize that the temperature at the tropopause is not necessarily going to give you an accurate internal entropy of the planet. And so what I think has been realized recently is that you have to consider what is actually going on in the atmosphere in order to make a connection between the tropopause temperature and the internal entropy. I don't think it's hopeless, because we have models for it and we do kind of understand a little bit how it works. And especially if we had a probe that gave us a non-degenerate, because the problem with remote sensing is that temperature and composition are degenerate. But if you have a non-degenerate temperature pressure profile and compositional profile, you could do a pretty good job at modeling it. The thing is, however deep down it goes, you might also wonder what's happening even deeper, because what used to be the conventional wisdom is that there existed something called a weather layer, that's very near the surface of the planet, and that once you're beneath the weather layer, everything's fine. And what we're increasingly discovering is that that might not be true. That gas planets might sort of be meteorologically active kind of throughout, but that's speculation. Yeah. Yeah. Mm-hmm. Yes. Well, okay. I will start by saying cosmochemically, we know oxygen is around. We also know other stuff is in Jupiter. So we've measured with the probe that there's methane. Well, okay, we've measured also water with the probe. We know that there's some water. The Juno mission, part of the goal was to determine exactly how much water there was. The problem with the probe is that it measured a subsolar quantity of water. And this is a little bit hard to wrap your head around, right? Because if you imagine how planets form, you imagine that they collapse out of the gas envelope, and also that they're sort of being pelted by solids, by planetesimals. So the sun we think of as basically a collapsing of that nebula, and how is it that Jupiter, which exists out in this environment where it should be constantly, and we know it is being constantly pelted by planetesimals and just accreted out of the same envelope, how could it have less ice? because we know there are comets and all these reasons to think it might be enriched. So what was thought at the time is that, well, you know, there's meteorology going on, and so perhaps the water is not uniformly distributed around the planet, and maybe we went into a region that's like the equivalent of the Sahara Desert, right? That wouldn't give you a good bulk sample for how much water is in the Earth's atmosphere on average. And so we do believe that it was a sort of meteorological anomaly that it went into called a hotspot. But troublingly, as we've found with MWR, ammonia also appears to not be well mixed, and we are sort of having trouble coming up with a very confident value for how much water is there. But there definitely is some. Yeah. Yep. Mm-hmm. Yeah, so it would have some implications for the evolution of the planet. So basically, because the core and envelope decouple, it's easier for the atmosphere to cool off at early times. So if you look at planets and systems of different ages, then you can imagine that you would see smaller planets. If you look at the evolution and size that's expected, you can compare the two models, right? You can say, let's imagine that this isn't happening, and let's imagine that it is, and how do we expect the radius to evolve as a function of time? And I think crucially in those first 100 million to a billion years, there are different predictions. So as we continue to get exoplanet statistics, we can see to what extent that pattern is reproduced. Now, a problem with that is it's not actually that easy to get a confidence age of planetary systems. The same work that I mentioned earlier by Will Missner and Hilke Schlichting is the reason that they're so focused on chemistry is because they're interested in tracers that would be indicative of this sort of chemistry happening, and also indicative of the process of convective inhibition. And they basically make two predictions based on whether it's happening or whether it's not happening for what sorts of observations that we expect for the composition of the observable atmosphere that can be detected by JWST. So those are a couple ideas. Another different kind of way of thinking about it is the magnetic field. The luminosity of the planet decreases by so much that it may actually decrease the convective activity of the core, at least early on in the evolution, sufficiently to shut off a dynamo. So if we're able to observe the magnetic fields of some of these exoplanets, which can be done with radio astronomy, for example, then and we find evidence that some of these young planets don't have a magnetic field that could or don't have as strong of a magnetic field as would be expected, then that could be further evidence. So those are just three ideas. Yeah. Thanks.